As we did with linear regression modeling, we now want to add the categorical sex variable to our model to see if we can improve our predictions even more. Remember that with regression, we had to specifically state that the sex variable was categorical. Our neural network modeling process won't take categorical variables. We have to turn them into numeric indicator variables, or, when we get to a multi-category variable, one-hot encoded vectors, to be used in our models. To do this, I'm using the mapping function of data frames to change my values of m and f to 1 and 0 respectively. As a precursor to our modeling process, I'm also changing the type of my variable from a data frame to a NumPy array. I will discuss why this is necessary on the next screen. We can see that the column with index 1 in my array has been transformed to zeros and ones through this process. Later on, we will use columns with indices 1 and 2, meaning sex and height, to predict the data in the column with index 3, or mate height. Now I can create my new model. I start with the sequential function as I did before, but now I'm going to add 2 dense layers to my model. In my first dense layer, I've included 2 units with a linear activation function. This means that each of my inputs, height and sex, will be fully connected to 2 hidden layers through a linear model. Then I add my second dense layer with 1 unit and a linear activation function. This means each of my 2 hidden layers will connect to my output layer, or mate height, through a linear model. I am again utilizing the atom optimizer with the mean squared error loss function. Note that in my fit statement, I am now utilizing multiple columns of data for my input variable. When I did this for a single variable, I could just call the single column for my data frame, and I had no issues with data type matching in this function. But now I would like to use multiple columns for my data set. This is why I needed to transform my data frame to a NumPy array earlier. Now I can call several column numbers, as in this case columns with indices 1 and 2, to help model the column with index 3. Again, you'll not generally be asked to extract and use the weights from our neural networks, but for demonstration purposes, I'm doing so here. The list of values becomes a bit more complex when we have multiple layers, but the general process of extraction is essentially the same as we did with a single layer earlier. Extracting the weights and biases from the model allowed me to create the diagram that you see on the screen that shows the specifics of the neural network that we just created. This graph was created using the GraphViz package in Python. The code to produce the graph has been provided to you in this week's code, but will not be discussed here. You're encouraged to explore this code further and potentially use it in your own projects. We can see that sex and height are fully connected to our 2 hidden layers. The 4 weights produced from linking 2 inputs to 2 hidden layers are shown next to the arrows that connect the layers. The bias terms that are included in the calculation at each layer are provided in the boxes above the node that they help to predict. Since we used a linear activation function at each point on this neural network, we could in general say that H1 was found by taking W1 times sex plus W2 times height plus B1. H2 was found by taking W3 times sex plus W4 times height plus B2. And mate height is found by taking W5 times hidden layer 1 plus W6 times hidden layer 2 plus B3. But doing a bit of substitution, we can create a different equation for m height that doesn't include the hidden layers. And finally, that equation can be simplified to the form that you now see on the screen. Essentially, we're getting a new weight for sex, which is made up of weights from both of our dense layers, and similarly a new weight for height made up of a different combination of weights from the 2 layers, plus a bias term. If this is the case, you might wonder why we use 2 dense layers to predict mate height when we could have simply used 1 dense layer. The truth is, you could, in this particular case, just do a single dense layer, but let's take a closer look at the output we get for the current model and what we would get if we were to create this neural network with just one dense layer. Here we can see that our model is converging on a form close to what we saw when we conducted the regression model. In training this model for 1,000 epochs several times, the loss usually came out to be a value around 8. So what happens if we just use one dense layer with the rest of our input staying the same? The graphical output looks somewhat similar, but isn't as good as the model with 2 dense layers. In repeated trials of running this model, I never obtained a loss any smaller than 11. It would appear that for this data, even though the 2 models are functionally equivalent, using 2 dense layers provides us with better accuracy when using the same number of epochs for training. This occurs because more weights and biases can be tweaked at each step to help reach an optimal solution faster. However, this method does take more computational resources, and we could achieve the same results with the simpler model if we just ran it for a few more epochs. In general, it's frowned upon to use multiple linear dense layers sequentially in a model, as they are redundant and could be represented with a simpler model.